Hello, as I said, part of this class is to try to give you a framework in which you can be successful in your future endeavors. Because you're going to be working in technology, it is therefore essential that you learn how technology is progressing so that as you're in the middle of it, right, as you're in the middle of this technology progression, you can pick out things and say, that's going to be something I need to pay attention to and be up on that technology before it actually happens. And also be able to say, you know what, this is going to happen, but not as quickly as people think, so that you don't waste time on something that is going to take a while. Or, whoa, this is happening now. I don't know how I missed it. I need to catch up on this stuff. That's a technologist, somebody who can really, really see what's going to occur. And it's easy to do, honestly. If you take the time to learn how technology has progressed, it'll help you see what's going on currently. And we'll adapt that a little later. So we're going to start off with some information about how things began and how the computer really, really changed things fundamentally. So this happened way before me. I'm not that old. And so I've had to learn about this stuff, and I found it very, very important. I've looked at it and said, wow, if I would have known that coming out of school, there's things I wouldn't have wasted my time on. There's things that I would have spent more time on. That way I would have had an easier time learning it and being able to put it into place in my work job. Lots of people in technology never do that, right? They just kind of keep their head down and they do what they're doing, and they're seen as the grunt worker. They're seen as the person that doesn't have the forethought but can get the job done. And really, I want you guys to be the people that have the forethought, that you're not just the grunt worker, you're somebody they can rely on and therefore get promotions and enable you to be more successful in your life. That's the idea. So let's take a look at what I've got here on the screen. I just pulled up the Word document that I put this into. You have it below this video. The development of the computer is one from calculator to new medium. So I'm saying certainly the computer starts as a calculator. That's what it starts as. But it goes into a new medium, and let's see what I mean by that. It is a new way to present information. Certainly the computer provides a new medium, but the implementation of computer technology into every aspect of our lives transcends the definition of medium. It changes and modifies, even combines medium of expressions. It combines communication methods. The internet is a child of the computer, which now is a channel to carry all other, if not all, mediums. So what I'm trying to express to you is, that's a very short way of saying it, is that the computer is a lot more than a calculator. It's a lot more than a channel that carries information. It has enabled a ton of developmental things that we never could have imagined. And so let's take a look at really, what did we deal with before? Well, there is a direct comparison that can be made from computers and books. The printing press was a big deal. By far, if you look at humanity all of time, the printing press mattered more than computers. And you could argue that computers never would have happened without the printing press. The idea is that knowledge is really important. And way, way, way back when, right, this is 1450, basically books were all handwritten, often by monks, and books were expensive. Knowledge was extremely expensive, and it was controlled. There was only certain people that had it. Now, you could say it was controlled by the rich. A lot of people will say that, but it was really controlled by the lack of technology. The fact that it took so long to copy off a book was going to mean it cost a lot, which means only rich people can afford it. And that, of course, would advance them, right? They read it, they got new ideas, they got new thoughts that spark other ideas, where poor people didn't have any of it. They didn't have any of those things. So when you now say, oh, you know what we can do? We can take these little letters and we can stick them all together, and we can make an entire page. We can format it once and keep printing and printing and printing and printing that page. Now, all of a sudden, the cost drops on books. Now it's a lot cheaper to get your hands on them, which means it's a lot cheaper to get your hands on knowledge. Some of you already then are taking a look and saying, hey, there is something that resembles what happened with computers. Right? So today you can learn whatever you want. There's books on everything. And in some countries, there are no computers available, but there are books available. And that's kind of a vital thing. And so we do deal with the situation where not having computers in today's age does stifle a person. No access to the internet, for instance. So the innovation of the computer predates the application of electricity. So what I'm trying to tell you here is that a computer is something that computes. 2 + 2 = 4. That's a computation. And you need to know that if you look at the history of computers, it's going to go way, 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 way back according to that definition. But we're not starting there. That's when we could talk a whole semester just about the development of the computer and not cover anything else. So what I really bring it to is during World War II. So during World War II, there was a couple of things that happened. And one of them that we didn't even know that happened until much later, until the 80s. So there was a man named Turing, and he envisioned, and think about how revolutionary this is. He envisioned a device that would be built to accomplish many tasks instead of one task. So as I described down below this, basically what you're talking about is if I created an engine that works off of steam that makes a belt go around, then all of a sudden I can put that, just those few concepts, onto a ship, and now the ship can move. I can put it onto a work environment and have a conveyor belt move to move materials up and down that. But it's still a steam engine. That's all it is. It's not something else. It's a steam engine adapted to work in many different ways. That's everything in the world at that time, by the way. You use a certain tool for this, right? And he's saying, let's develop a tool that can actually do a lot of different things, not just one thing. That's like a whole different line of thinking. Well, he actually builds an electromechanical code cracking machine. So the English were big into how can we thwart Germany in every situation. And a lot of people really don't understand what's really going on here because we talk about different countries. But it would be like saying, in between us, Arizona, the good guys, and Texas, the bad guys, is New Mexico. And that's it. And the honest truth is it's not even that. It's like half of New Mexico, right? So Germany is right next door, and they want to kill you and take over. And so they're throwing everything they can at trying to thwart that, trying to make sure that they can't get that done. Well, part of it is that the Germans had an encoding machine known as Enigma. And so they would send all these messages that were coded. And so every time you intercepted a message, you didn't know what it meant. One of the ways that we might be able to decipher what's happening here is if we had some kind of machine that operated a lot faster with calculations than we did and could go through the code and say, there it is. Now, the truth is, just to sum up what happens, that his machine never really does what it's supposed to do. They end up cracking Enigma because they get one of the machines from Germany, and there's lots of movies, not lots, but there's some movies about that. And so they know what the Germans are doing, and they have to really try hard to make sure the Germans never figure out that they've actually broken the codes. But this was really a huge beginning. Now, across the ocean in the United States, there was the same kind of thought process going with a different problem. The problem is that they had made massive guns that sit on massive ships, and they didn't know how to target them. So if you watch World War II, you have a few people on that ship, on that vessel, that are trained to fire that cannon, and they have to try to figure out, where am I firing this? How high do I make this in order to hit the ship that's out there? And that's why those sea battles were such a toss-up, we'll just say, because America, I don't know about Japan, but America did not have, that's this many miles away, so just bring it up to this level and fire it and you'll hit it. They didn't have any of that. Those are tables, ballistics tables, and it was going to take a long time to actually create ballistic tables that somebody could use. So in the meantime, people are out there dying, and they don't like that idea. And they're trying to figure out, how do we make this not happen? And one of the plans was, let's build an electronic numerical integrator and computer, code named ENIAC. So we'll make a computer, and that thing will be so fast, we can just set it up and it'll calculate that stuff for us. It's the idea. And I always kind of start here, really, because it was fully electronic. It was fully electronic. Now, we use that term so much, people, they use it interchangeably with like computers. If it's an electronic thing, it's a computer. Or they say electronics, right? The board on inside a machine is electronics. And so we kind of have gotten away from, what does this mean? It means it runs on electricity. It's got electrons flowing through it. And that's the only way it works. There's no physical part that does any kind of calculation. It's all electronic. And so they began to try to use this. And it was the first one that had conditional branching and nested subroutines. Now, I know you're probably in an intro computer class. You may not have gotten to this point, but conditional branching is, if this is equal to that, then do this. If it's not equal to that, then do this, right? There's a condition and it branches logic from there. And then nested subroutines are part of that. Okay, so if that's true, then I go into the subroutine and then I deliver it back into the regular code. And so it was the first one that had that ability, and that gave it the ability to be programmed to solve different problems, not just the one problem over and over again. And I give you some photos. This is really what it was. That's what it looks like. In the beginning, basically you had some men working on it and a lot of women. And we get into this class. There was a lot of women working in this, and a lot of them coming from mathematics. All right, so once the ENIAC really makes its mark, then it becomes like, hey, where could we use these? Because you're really dealing with a machine that they actually called them electronic brains. They were like, in people's imaginations, there were these wild things. So if you watch any of these old 30, 40 movies, right, there's all these lights going on and the thing is just this magical thing. Well, because they were so expensive, you really could only buy one if you had the money. And so they were used in census calculations. They got to the point in the US where the US was growing so fast, they were not able to do the census calculations before it was time to take the next census, which is every 10 years. So they couldn't get it done. A computer was a perfect fit. In a lot of big businesses, payroll was just this massive thing. You would start payroll the day after the last time you did the last payroll and work on it until you could get that out. And they would hire tons and tons of people to make that happen. And then, of course, in banking. So in banking, this is interesting. Computers, the term computer was used to describe this thing that could be programmed in many different ways. But prior to that, you could have the job of a computer. You would be a computer. So in other words, you would go in and you would be part of a bank, and they would say, you handle this account because that account's so big that it'll take up all your time. Or maybe they had 5 people on one account, or maybe you handled 10 small accounts, right? You were a computer that was handling all the computations. They bought this and they did this and that kind of thing. They came and withdrew this money. A person did that computing. So it's kind of interesting. It's kind of a misnomer, as they say. We use the term computer, but it does a lot more than just compute, because that's what computers mean. It means I just do calculations. It does a lot more than what we thought. So maybe a processor would be a better term. I mean, there's lots of things. Now, and then, of course, today we use them for everything: traffic lights, spreadsheets, documents, payroll, taxes, and so on. So while a new technology in any age is expensive, computers at the beginning were so expensive because they were filled with wires and components known as vacuum tubes. And we're going to get into this a little more seriously in another presentation that you'll watch after this, basically. But these vacuum tubes, in a very, very simple way, is like saying a light bulb. And really, the whole idea comes down to this binary. Right? People hear that term and they know that computers they run on binary, or that's how they know what's going on. And that's basically that there is an on or an off situation. Because we're dealing with electrons, we're going to stop the flow or have the flow. And the honest truth is that it's usually really, it's this voltage or that voltage. It's not really an on or an off, but we like to say on or off. So that's how you could have a physical one, right? You could have a mechanical switch, click, that's on, click, that's off. So we talk about it in the flow of electrons, but everything could boil down to this binary. Well, how does that fit into vacuum tubes? Well, vacuum tubes would be a representation of a 1 or a 0. So if you had 8 vacuum tubes running across here, you could have lit, lit, not lit, not lit, 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 not lit, not lit. So you'd have 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. You'd have that listed out. It's ones and zeros. Since you got 8 bits, you got a byte, right? You got a byte. So that is, you know, a simplification of how that works, but that's how it works. So when you look at, I've got my little table here. ASCII was one of the first standard encodings for a computer, and that was America's Standard Code for International Interchange. And you can see it's very simple. This is only part of ASCII. That's actually more to it than that. And you can look that up. You can look up an ASCII table. We don't use ASCII anymore because it doesn't really provide for what it says it does. It is providing information exchange, but it's not at all information exchange that's worldwide. Not everybody uses these letters, right? So a 0, though, to represent a 0 on your screen or in a calculation of some form, you would have to have in binary off, off, on, off, off, off. So 4 bits is a nibble, and 2 4 bits, yeah, 2 of them is, oh, I need to change that. 1 4 bits is 1 nibble, and this is, I need to modify that. So sorry. And then the second 4 bits is a nibble, which equals a byte. So I guess I do have that right. I say 1 4 bits is a nibble, second 4 bits is a nibble. So that is true. And so you got a total of 8 bits that you're dealing with to equal any of these letters. So you can look and say, well, what is A? That is 0 1 0 0 0 0 0 1, and that equals an A. That's actually coding. That's actually coding. So we call programming coding because it's cool. It gets a lot of buzz. Oh, I'm a coder. Well, you're really not a coder. So we call the programming, we call it programming code. And so that's been shortened to code, which means if I code, then I'm a coder. And that's not really what that means. This is what it means. 0 0 1 1 1 0 0 0 represents 8. That's a code. I'm talking to you in code. If I go 0 0 1 1 1 0 0 1, and now if you understand binary or ASCII conversion, you go, oh, that's a 9, right? That's actually coded. So anyway, those vacuum tubes had to hold that, which meant, and I don't think I have another picture of this in there, which meant they were massive. In order to create the logic, so notice all these wires, this is the programming. There is no terminal where somebody's writing, coding, programming something. They are basically taking this plug from this logic over to this plug from this logic, which now makes this. So it's a way of physically programming the computer. And you can see these racks of vacuum tubes, but each one of these, you'd pull them out and they'd be racks of vacuum tubes in there. And so that's how it worked. They're actually programming it with these wires. Wow, you know, that's hard. That's hard to do and took forever. But the results, right? The results were amazing. So that made it worth it. That it's just the thing could compute so fast that it was just like bam, done. So once they got that program set up, right, then they're going to run as much through that program as possible before they have to do something else. All right, so let's go down. There's some vacuum tubes for you. If you can get one of these big ones, right? Vacuum tubes are available. I've got some here that I show you in the other video. But if you can get some of the old ones, they're worth a lot of money. If you ever see vacuum tubes that are actually on a rack, because this picture is not showing you the full rack, yeah, take them, you know, buy them. All right, then we move to transistors. And we'll talk about the implication of this. Well, we'll just talk about it now. So transistors are very small, and they're roughly 40 times smaller than the vacuum tube. And so it's really like a little tiny thing right down here, replacing this entire huge thing. So you're using less power, and you're also now can make a much smaller computer. So while it was conceived in 1926, which means somebody said, you know what, I think we could wire something up electronically and it would be about that big. I think we can do that. It was actually implemented in 1955. And that began to really affect things. So you went from a computer taking up a room to a computer that takes up, well, as big as my office, right? Much, much smaller space. But they had a problem. How do you connect all of it together? See, the thing is that the underlying thing that's going on here is that you are creating circuitry connections between these components in order to make it happen. As a matter of fact, a student was showing me just the other day that the first Pong program that wasn't actually programmed in software and then running on a CPU, it was programmed in the logic of the circuits. So where it was going actually made it happen. So in other words, taking this massive process and boiling it down to something that fit in an arcade cabinet. So it would have fit on a panel about that big, a big motherboard. And so there wasn't a processor that's running some program that makes those lines move back and forth and a little dot bouncing around in it. It was actually in the logic of the circuitry. And so when you are looking at, wow, we've got vacuum tubes that are providing that, and then we make something 40 times smaller than that and transistors, wow, now we can really get into something, right? Now we can really program some powerful computers, or I should say build, not program. We can build some powerful computers, but the manner of connecting it with all these wires was a nightmare. And you would have potentially one transistor with 18 different wires coming out of it to different locations. And they could think in their minds logically, now that we understand how to build a computer, how to make this logic function with these physical components, we can diagram something out and say logically this is how it's going to work, but we don't have the actual physical components to make it work because of this tyranny of numbers. That was used to describe the problem with I can design it, but I can't build it. That one transistor or a set of transistors that becomes the hub for this are going to have 48 different wires going in different directions. It's not going to work. One, it's too hard to actually, manipulate it physically. Second, every time you've got another connection, you've got to have more power to send it through that. It was a problem. It was a real problem. And so what ends up happening is a couple of people, Jack Kilby working for Texas Instruments, you know them, and Robert Noyce of Fairchild Semiconductor, which you don't know, they ended up getting bought out and absorbed and so on, created the integrated circuit. And I say it is an accepted fact now that Robert Noyce created the first IC circuit with Jack within months of it. And some people will still argue about it. They'll still say no, because a lot of books will say Jack Kilby created this and you never hear about Robert Noyce. And it was just like, basically they talked to reporters first is how that went down. So these people both have the same idea is what I'm saying. And they integrated all that circuitry. That's what an integrated or an IC refers to. I have mapped this out of how this should work. This is Pong. I've mapped it all out and it's going to go over here and here and here and here and here and here. And that's going to be the whole thing. Let's take all that and put it onto a chip, a single die, as they call it. We will integrate the circuits and put them right onto the chip. That's what we're going to do. So you're going to wire the components together through a layer of metal that's evaporated onto another structure. And you can look up more on this, and it's pretty dang cool. It really is about layering this, and it's a dangerous process. That's why people usually are not around when this is happening, because you're using chemicals that will kill you. But you're layering these circuits on top, and then you end up with using something like silicone, which is a semiconductor, meaning it conducts in some situations and not others. And now you can have this gate that when it has a certain signal on it, it's on, and when it doesn't, it's off, right? It can do that, which is fantastic. Now you're getting to the size of a fingernail, right? A whole computer board was reduced to the size of a fingernail. Further, the ability to design and make the same chip over and over now becomes available. So before, you would have said, here's all my components. Now let's hire a bunch of people and they're going to sit down and wire the components together. And so when you're building a computer, that usually was basically take your refrigerator and chop it in half. And the lower half is now that computer. It's still, pretty big by today's standards, but you're saying a person has to wire all that. Person's going to sit down and they're going to follow the schematics and they're going to get the soldering gun and they're going to put the wire right. They're going to do that. And it's going to take forever to build that thing. Increases the cost, increases the time it takes to get there. So not only are we taking, okay, we no longer need to make all those wires, we can actually lay that into a single chip. So we smash that down even further than we thought we could go. But now we also can, once we do that, print 1 million of them. We don't need to stop printing them. We can print as many as we like because we did all the work once, just like the printing press. We set up one page, now we print 1,000 copies. Set up the next page, print the second 1,000. That's the way it was done. So there really is a couple of ways that you can look at the printing press and what it did to society and how it actually functioned and say the computers did the same thing, except on steroids, right? All right, so basically the big computers were doing the jobs that they were built for, and everybody that was using those didn't want smaller or more powerful parts. So there was a certain amount of, this is already set up and running. We use it for payroll. We use it for scientific calculations. We use it for census taking. We're good. I don't need a new computer. Yeah, but this one's going to be smaller and more powerful. What am I going to do with it? So it was already doing jobs, and the people that you would have thought understood it didn't. They didn't understand it. And that's an important key principle that we'll go throughout. This is the first one. Here's an early integrated circuit and what it looks like. And this is what we're dealing with. This Core i7 is actually probably, this picture is about 8-9 years old now, but wow. When you look at all of this, that's all the integrated circuits sitting on that die. And over here, we've got, there's a line here. This line goes to there. It's very, very, very powerful these days. So the use came in. So for almost 2 years, no one used these integrated circuits. Think of that. It's like, holy crap, look what we did. And then nobody's using it. But NASA needed a small computer to use in a small spacecraft carrying 3 individuals to the moon back. Now, just to pause, there's a lot of people that actually think that we didn't go to the moon, and it's a big conspiracy theory, and they point out all this crap that's not true. The truth is we went to the moon. You can watch Mythbusters on it, and they just totally debunk everybody that says, oh, this, and this. But beyond that, why in the crap would you come over and say, oh, yeah, we need this really small computer, and that's what's going to be light enough for us to take in this lander? Why would you even go to the trouble of doing that? And people say, oh, well, that's how deep it went. It's like, that's stupid. That's a dumb thing. You would just make something look like it and pretend that that's what it's doing. You wouldn't actually spend the money on it. I mean, the government's not going to, somebody in the government will steal the money before they'll spend the money on what they should, right? So anyway, ICs were used for guidance in Minuteman missiles, Minuteman II missiles, Polaris missiles, and jets. And of course, they were used in the lunar lander. And if you ever watch any video on that, you can see that they often will flip through a book and they'll hit certain things. And at that point, not all the programming could fit, and they couldn't put all the variables in. And so they would have to get to a certain stage and in space, type in the program exactly, not missing a thing because your life depended on it. That's a very scary thing. And so when you watch any of those old videos of them, that's what they're doing. They're programming a computer. And of course, they didn't think up the programming. Somebody laid it out for them, but still, don't get it wrong. This, hit this key, hit enter, this, hit this key, hit enter, right? Whew. while you're about to land on the moon. Anyway, so in 1960, the first IC had fewer than 10 transistors on it and cost $1,000. 10 years later, the cost of making an IC had dropped to mere pennies and were thousands of times more powerful. So making an IC now, pennies, and they're 1,000 times more powerful. Within how long? 10 years. 10 years later, you're dealing with something that was massively expensive to now it's only a few cents. That's going to affect things quite a bit. So in the 1970s, integrated circuits were available and sitting on shelves, ready to be used in personal computers, but they had not been built yet. It would take individuals with vision to bring this power of the computer to us, to the person. These visionaries did not come from established computing fields. So in other words, they weren't sitting in NEC or any of these places where these massive computers were being built. Instead, they were individuals that were driven by their own desire. And that is commonly always the way innovation works, is that the people that are there that have been working with computers their whole life, they don't see what's happening and they don't see how that's going to influence things. Somebody else that looks at the way things are and says it could be this way, they come in and actually design. And so there's the general specific part, which I already talked about. So we'll just skip that and come down to the hobbyist. So what really things get boiled down to a lot is a couple of people, right? We tend to do that in history. You know, that person said that, even though there was 1,000 people involved in what was going on, right? This is the same thing. Everybody was doing this. I wasn't. I'm still too young, way too young for this. But you had all these parts, and being able to take electronics and then build your own logic and make a computer that does something really appealed to them. Just building your own calculator. Calculators were expensive. And so if you were a person, electronical engineer, you could understand how that worked. They were putting it together. So there was hundreds, if not thousands, of people that were getting their hands on these little parts and making something out of it. And of course, some big things happen from that. And I'm going to dig into each one of these, not at this time, but this is just a little tiny bit of information. Basically, you deal with a Bill Gates and a Paul Allen. And these guys met in high school. It was a private school. Bill Gates was rich before he got Bill Gates rich. And they bonded over the love of programming. Now, Bill Gates is like 13, Paul Allen's like 17, you know, so there's some differences in there. But see, they got to use the school, had access to a mini computer. Mini computers, again, half of your fridge, big computers, through a terminal on campus. So because they're rich, they get access, one terminal, to the city computer. That's basically what they do. And the dude actually, I'll get into it more later, but he does some incredible things. He was a genius programmer. He really was. And Paul Allen was really good too. Now, other things were happening, right? Steve Wozniak showed off the first iteration of the Apple computer at a show where all these electronic geeks would get together. And he really wanted to upstage everybody. He really wanted to show, look what I did. And his computer was awesome. But when I say computer, it was just really a board that you had to plug a monitor into, and you had to figure out your storage. You had to do all that on your own. Well, how did he get in here, right? Well, leading up to this, Wozniak helped Steve Jobs at Steve Jobs' job for Atari. And they were asked to actually decrease the number of chips needed for a new game called Breakout. So this Breakout game, so they're programming in 1973. It's going to be a stand-up arcade game because Atari really pioneered that. And so they had already figured out the logic. This is the way it's going to work in this arcade system, but we're not going to make as much money as what we would like. So you interns that are getting paid crap, you figure it out. Well, it was really Jobs that was put on that, because Jobs basically said, hey, I can do that. No problem. And then, of course, he struggled. Wozniak was an electronic genius. He was, probably still is. He's still considered the whiz, right? He's the Woz of the electronics, just a genius in the things that he did at that time. And so anyway, he reduced. So Woz spent some time. They worked together. So I'm not trying to say it was just Woz. They reduced the number of chips needed by 50. That's a lot of savings. So even though these chips are costing money, you're talking about by the time we get done building this, it's going to cost $100. And then we're going to try to sell it for 200, and we're talking 1970s money. So if we can reduce it and we take 50 chips off of that, now we can sell it for 45. I mean, build it for 45 and sell it for 85, and we'll get more sales, right? That's what happened there. It was so ahead of his time that those at Atari didn't really understand how he did it, right? So you're talking about really smart people just going, it works. I don't understand how he got that done. And of course, that would later give him the skill to deal with the Apple computer. Now, why did he want to do this? What was his motive for actually getting that done? Why did he spend any time in electronics and so on? Well, both Steve Wozniak and Steve Jobs, that lived in the same neighborhood, their fathers were actually engineers. So they were people going down and using these massive computers. This idea of computers was in their DNA, right? It was from them as a little kid. This is what my dad's doing. This is what my dad comes back and talks to me about. And I think someplace in here, I actually tell you that Steve Jobs is actually, Steve Wozniak actually has gone on record as saying, I built the computer because I had told my dad that someday I wouldn't own a house. I would just buy a computer with that money. That's how much he wanted a computer, and that's how much a computer cost. And so when all these electronics are sitting around, he's automatically, as a teenager, thinking, how do I make this happen? Right? How does this happen? A lot of the movies really are like, oh, these were a bunch of hippies and they had all this free love, and so they shared their free ideas together. And it's like, yeah, it sounds like you're a journalist. That's what that sounds like. You were smoking too much pot at the time, right? What was happening is you had engineer families, engineer kids. They had seen how this stuff works. They wanted it for themselves. And now the electronics are sitting there that enables them to do it. But I love to point out that in the Christmas of 1975, Atari released a home version of Pong. You could buy it and run it in your house instead of right here in a machine. And then later, right, this is the 2600 with the Space Invaders that is so popular, right? This becomes a platform for home and play. 1975, really kind of, how should I put it? Basically, the first real use of a home system was for games. That's just all there was to it. This is the video computer system. It was called the Atari VCS. Later on, they renamed it to the Atari 2600. But the idea was, this is a computer. Now, yeah, it did only play games, but you could plug in a cartridge here and program. You could do other stuff. It's not something they thought about originally, right? They cut everything out of this to streamline it, to make sure that it could be sold as cheap as possible. But lots of people wanted to use it as more than what it was. And so when you look at 1975, buy that for your house. And when did Apple release? 1976. And a full computer, late 1977. So the first real computers were really video game machines. That's really what they were. There was plenty of different kinds that we'll look at in a second. All right, so then massive things happen here. When a company called MOS Technology comes out, and they make this chip called the 6502, and there are websites devoted to the 6502. It was an 8-bit CPU. Many of the ones before that were 4 bits, and it ran at 1 or 2 megahertz, not gigahertz, so that you can have an idea of what's going on. Now, MOS Technology was originally created by Alan Bradley, and there's a character called Alan Bradley in the movie Tron, and that was who he was representing. And so, in 1969, to combat the monopoly of Texas Instruments, because they held a huge, massive share on making chips, right? They made them for their calculators, and were really kind of one of the only places you could go to get these computer chips, and it was a problem. So MOS kind of, Alan Bradley is like, we have to go to these guys, and they're upselling it, right? They're basically saying, we don't want you to be our competitor, so we're going to charge you more. So they started their company. 1976. And so in 1976, sorry, in 1969. In 1976, a company called Commodore purchased them because they had a calculator business and they were getting their butts kicked by Texas Instruments, not because the technology was better, but because Texas Instruments made all the chips that went into the calculators. And so, if you're going to compete with us, we're going to sell you those chips at a higher price. That way your calculators will always be more expensive than ours. That was the idea. And so there's the 6502 AD. They had a 65C and so on that were basically different options, or faster processors and so on. But Jack Kilby, I should back up here. The Commodore guy, he bought out Moss so he could own that. And it wasn't Jack Kilby, but we'll talk in more detail of Jack Trammell, who had that business. He decided, you know what, I don't know what to keep out of this company, right? What I need is chips for my calculators. So do I need everybody? And usually when there's a merger, that's what happens. There's a bunch of people that get fired. So he's calling everybody in and saying, what do you do here? How does it contribute to his goal of making calculators? So Chuck Peddle comes in, who was pretty young at the time, and he understood there might be an interest in something that would later be called a PC. So they produced the first single board computer in 1976. This predates what Apple did. For the first all-in-one computer containing a computer itself, a monitor, and a keyboard, and storage, being sold in 1977, with Apple II being sold a little later that year. So they kind of beat Apple to the punch. And guess what's in the Apple computer? And we'll get into this a little more. The 6502 that Moss makes, that Jack owns, right? So Commodore, this computer right here, awesome design. I mean, that's like one of those future retro things. People are buying up these things, even though they don't even know what they are, because they're kind of a future retro type look. But basically what ends up happening is Chuck is like, hey, look at this board. And I think people are going beyond calculators. And Jack gets it, right? He's not a computer guy. He's not an engineer, but Jack's like, I think you're right. So let's do the board. Let's see how well that goes. Oh, it goes really well. Let's do a whole system. Somebody could buy the whole system. It'd be like a computer for their house. And the name of this is PET because it's personal electronic transactor. See, Chuck felt like a computer. It wasn't really descriptive. So he called it a personal electronic transactor. And that really starts this big fight for who's got the home market. And the Commodore 64 goes on to sell 19 million units. And he really was at the heart of that, the founder of Commodore, because he believed in, and he would always say this, computer for the masses, not the classes. In other words, make this as cheap as possible, as powerful as possible, so everybody can have one. And when we get into him, you'll kind of understand why he was doing that. But that's a fundamental thing that changes what happens at this time. That's a fundamental thing. So Apple Computer was, because it had a floppy drive, was more capable. Various Apple II models sold for about 1.2 million. So you're dealing with 10 to 20 times more Commodores were sold at that time. So here's kind of a, the way it would look, those two systems in comparison. And just to let people know, what's going on here. The 6502 was such an incredible invention, such an incredible system. It was used in Apple II. It was used in Commodore's machines, obviously. It was used in the BBC Micro, which was all over in England. The Atari 2600 used it. The Atari 800 used it. Nintendo's NES used it. And the Tamagotchi Digital Pet used it, if you're familiar with those things. That's how much this design from Chuck Peddle and his team really changed the world. It was put into so many things, and how Jack in particular changed things, because he didn't do what Texas Instruments did. As long as there was enough chips for his stuff, he sold it to other people. And so you could really say Apple would not exist without Commodore selling chips to them so that they could sell their computers. He didn't believe in smashing that. That's where we're going to end this video. This has been long enough, probably one of the longer videos that you'll have. And we will pick up here in the business use. So we'll talk about that. I'm going to pick that up right now. But for you guys, you'll watch it when you can. Thanks for watching, and we'll talk with you later.